don't be disappointed for chapter 8 because it covers whole structural dynamics in a few pages. Here, what happened to Hyunchul? Who else is missing here? Kyung-suk is here. Hyunchul is the only one? Oh, Bong-sik. What happened? They didn't tell me. Okay, response of structure. As I survey Monday, most of you took the course on vibration. Vibration is not identical to the structure dynamics. The art of the vibration is a subset of structure dynamics. But one time or another, even if OSE has a variety of students majoring even electrical engineering here, then chemical engineering here, and mechanical, aeronautical, all that. But when I teach in the Naval Postgraduate School, we have a psychology major, undergraduate, education major in undergraduate, pursuing the master's in mechanical engineering. What do you think? It's very difficult. They have a tough time, but those years we had a program for 2.5 years. In 2.5 years, they did very successfully, but they are taking the 4 straight courses throughout the year, and in addition, they have to write a thesis. So day and night they pursued. It was very successful. I never saw anybody who failed. One person, one officer who failed under my supervision was, he couldn't get the minimum 3.0. Then he got 2.98. 2.98, if you round off, it's a 3.0, that's good enough. But in military, 2.98, you can't graduate. So that's why something like over 110 students under my direction, he couldn't get the degree. That's what happened. What happened is that's their rule. So that was a pretty sad moment. But here, we have a variety of students. If you didn't take the vibration class or structural dynamics class, I think you have to rethink to take that course. Because without the dynamics, just getting statics is not enough. Dynamics, you have to learn the basics to have a successful career. So this is a response of structure. Section 1, dynamic response. So dynamic response and static response, what's the difference? All the ship designer, they use a skill called statics. In the past time and the present time, I really don't know detail in Korea shipbuilding business. In US, everything was based on the static analysis. No dynamic analysis for designing the hull thickness, all the internal structure design, they use the statics. And they use so-called the safety factor. Safety factor is a static concept. Not static concept. It's part of the static analysis, which is multiplier. So safety factor, the naval architect, they apply to strengths. They divide the strengths like a yield strength or yield stress or ultimate stress divided by the safety factor to reduce the strength or stress, which is not very good practice. Instead, you must multiply the safety factor. Sometimes I call that as a fuzzy factor to the load, because the load and you have to compare the actual the stresses. Then you have to compare. You have to calculate and compare with the ultimate stress or the yield stress. Then you can declare, oh, this is safe, this is not safe. But in that process, if load and strength of the material, if it has a nonlinear relationship, then you got a problem to apply the safety factor to the strength by dividing. That's very important. So you must always apply the safety factor to the load, then calculate the resultant stresses, then compare with the yield stress, allowable stress, whatever. Otherwise, everything could be messed up. Like a buckling load situation, that's a nonlinear relation between the load and the stress, so vice versa. So that's what's happening. All this static-based design, if you ignore the dynamic, what's the problem? Stupid question. Youngkyun, what's the problem? What's important in the dynamic design and dynamic-based design and static-based design?
I think it has to have a time. Just one time, some period.
When you say dynamic loading, what kind of the terms involved in dynamic loading? Important thing is inertial force, for example. Inertial force, mass times acceleration. For static concept, you don't have mx double dot. That could be very massive. Do you have kx? You call that's a stiffener loading or spring loading, right? That's easy. That's a static loading, you can treat that. What about the damping loading? mx dot. For the static concept, you don't have x dot. So you don't have, in static loading, you don't have mx double dot, you don't have cx dot, which means you just ignore. You can't do that. So for dynamic loading situation, you have so-called the dynamic amplification factor. At some frequency, the deformation for such a simple model, mass spring dashpot model, right at the resonant frequency, usually that's close to the natural frequency of the system. The response amplifies for that. That's a very detrimental usually. So that's what happened. So here in chapter 8, author is really dealing very simplest model in dynamics, mass spring model. Just one single degree of freedom model. Whole chapter 8, only 13 page. That is all he did, but you know, that's not all. But introducing very simple concept on the structure dynamics, but you must know, and most of you know, I'm pretty sure 100%, what the vibration is, what the structure dynamics is. Before you graduate, I want to tell you at least to take one course. That's very important. So dynamic response. And section 2, load from gas explosion. Don't be disappointed as you read this section, not much. Because it depends on the type of the fuel, everything changed. And configuration changes everything. It's not simple gas explosion in the open environment. Sometimes partially closed, fully closed. It happened in the tube, vice versa. And the damage level, we'll talk a little bit about that. Damage to building and domino effect, which is really, I can say, close to progressive collapse. In the building, for example, if a deck, due to the explosion, if the deck collapses, then progressively, as a result of the collapsing deck, then war could be, next moment, the wall could be collapsing. Then as a third part, the whole thing could collapse. And if the one critical structure member collapses, as a result, an other part can be collapsed. As a result, other part will be collapsed. It's a domino effect, it calls, okay? Progressive collapse. This is another, not really mechanical, general, the structure mechanics and simple mechanics. There is an art called the progressive collapse. Domino effect. People, and the effect on the people. For gas explosion, it gives a direct impact to the people. But you see the accident situation, most recent accident is a Busan accident. Few people really died as a result of the accident, and few different things you can remember, but this section, this chapter tells some story, not much story. So to predict explosion pressure is a one step in the consequence analysis. The next step is to estimate the response of the structures subjected to the load from the gas explosion. It's very easy to say. It's very easy to say load from the gas explosion, but there is a difficulties to define the loading. So here, in our opinion, there is a little information available on load and the structure response as a result of gas explosion. But don't feel, geez, what I could do. But since 1985, there are lots of publications available for all different types of the fuel. Then you can really explore internet. You will get lots of information for the particular environment, for the particular loading. So it's not really disastrous. Objective in this chapter is describe the difference between the static load and dynamic load acting on a structure, two basics. Explain how the load from the gas explosion act upon a structure. Describe the typical, the damage and the response of the equipments and the buildings when subjected to explosion pressure loading. Explosion pressure loading. For gas explosion, you are considering the flame effect also. The fire effect, temperature effect that you have to also consider. And section 1, dynamic response, is concerned. The gas explosion is a very rapid event. In a large gas explosion, the overpressure duration with typically, this is something like almost a 2-minute duration. Could be longer, depending if it combines with a fire. It could be, duration could be longer than 2 minutes. So this is a millisecond. You divide by 1,000, then you will get the second. Then you divide again 60, then you will get the minutes, about almost 2 minutes. But duration really varies. Duration of the loading for gas explosion, don't think it's only millisecond. Chemical explosion, high explosive, is less than 3 or 4 milliseconds. Everything is all done. Loading is done. But for gas explosion, no. If it coupled with the flame, fire, it could go more than 2 minutes. Could last 10 minutes. So that's what you have to think. Explosion, gas explosion. But this 2 minutes maybe for gas explosion. For explosion, maybe okay. I was going to draw all that, but it's too basic. I'm not going to bother to do that. Just to capture the concept here again. But whoever faced for the first time, this is about the simplest you can think of. This is like a gable frame, the house or buildings, whatever. Then you can convert into the simple mass spring model. So mass and spring. Here, no damping is included because damping dissipates the energy. So if you put the damping in the model, then response is slowly reducing in the exponential fashion. So this model, this prototype convert into the model as a pressure here, shock pressure, and this is mass of the building. So building times, what's this? Building mass is simply saying mass is m. This is pressure is loading. And this column you can replace as a stiffener. So mass spring model. And this P is pressure times exposed area is a force. It's a time domain force. So that's a dynamic loading. Okay. Then if you write equations of motion for this simple model, this is like a fixed model. You could make it more complicated. If base oscillate, like earthquake loading, sea wave loading, that's a time-dependent displacement you have to introduce. So if you write the equations of motion for this model, what is it? Who took the course? vibration. You took the course. What's the equation of motion? Sorry to ask you two basic equations. Mx double dot, right? Plus Kx is equal to F, right? F here is this is a triangular, the pulse, you can say, shock loading, you can say. So that's what that is. Mx double dot plus Kx is equal to the F, which is time the varying loading, and that's what you have to solve. If you have, if you consider the damper, which you dash pot damper, then you use usually C. C unit is what? C unit is the velocity term is involved, right? So Cx dot is what the damping force, which dissipate the energy. And here is no damping in the system. So it reduced down to the single degree of freedom system. Usually, you know, you can handle all the multiple degrees of freedom. And you can use a finite element model to generate, or finite difference model, depend on the system you are dealing with, whether it's a fluid system or it is a structure system or combined system. You can introduce those models. In structure system, as you know, which is most popular? Finite element method is most popular. And this is a result of the single degree of freedom system. And over here, this is a displacement, which is x dynamic response divided by the static response. Then you know this is like a static response. This is a dynamic response with a different TL, okay? And dealing with the ratio, over here, the T is duration, which is a fundamental period. T is equal to 1 over F, right? Right? T is for single degree of freedom system, you have only one period, which you can say T, right? T is 1 over F, 1 over fundamental frequency, right? And 2 pi F is equal to omega. This is all the first lecture of the vibrations. Don't look at me like that. Which is all that stuff. Right. So then it shows this is really fundamental. The period is very long. This is a fundamental period is a little bit higher. You can compute all that, but virtually solving the equations of motion for single degree of freedom model. So this is the case. DFL here is, they use a slightly different naming. This is the DLF is as shown here, dynamic load factor or dynamic amplification factor. They use all different names, but for the dynamics, the response amplifies. That's what it really shows here. For a triangular pulse in this type, this is A, the response goes like this. This is a TL over the T is a fundamental period. So I don't want to even T, basic equation for vibration frequency, right? Period, right? And 2 pi f is equal to omega radian per sec. This is all the beginning of the vibrations. So here you can say f is equal to omega over 2 pi. So you can do whatever. So for different poles, then you can see this. You can compute all this very easily. And one book I suggest, if anybody has interest to study continuously for dynamic response, dynamics of, I think it's the structures. And written by Ray Clough. This is now I think he retired, and there's a second author, Penjian. Second author name is, I don't remember exact, Ray Clough, UC Berkeley. UC Berkeley professor. I think he is now, I think, all retired, but book is keep revising. I happen to have a most recent edition. Very, very good book. It's very easy to read, but one of the best book. There are a couple more, but I have a few books, but this is a very thick book. So if you want to study, this is the one you may consider. And all the derivation of necessary equations for the all this kind of the pulse, the loading, you can look at it. And loading from the gas explosion. So the gas explosion will generate high pressure and often also high flow velocity. Of course, it is the pressure and flow that cause dynamic load on the structure and consequently cause the damage. And this kind of the pulse, have you remember we saw this before? Never? You don't remember? I think you saw this in the deflagration chapter. And the typical, the loading pattern, pressure as a result of the gas explosion. So here, this is a duration. Gas explosion, as I said, the duration really varies. For chemical explosion, duration is fixed, almost fixed. And peak pressure, positive impulse is area under the loading, and the positive is compressing the system structures, and negative impulse is pulling back. So it has such a combination for the pressure loading. Okay, typical the pressure loading. And this is the drag loading part. So which is CD here is, what's the CD? Drag coefficient, right? And A is exposed area. This is half times rho, the mass density. u squared, u is the velocity component, okay? So that's what the typical, the drag force is what that is. But the equation is nothing but just based on the basic principle, but question is how to predict. How to predict, I don't know whether flag can compute all this or not. That's we'll discuss with Professor Han next Monday. Hopefully Monday or Wednesday. So this is for situation, some situations here for the pipe loading situation. You can take a look at. And this is, I briefly mentioned the other day about this. Reflection of the shock wave when it hit the wall head on. So, of course, this is a shock wave as a result of gas explosion. U is the flow velocity. Is much higher than zero, of course, is shock situation. But in front is zero, everything is calm. That's what the explosion situation is. As hitting it, then in front of the wall, which means rigid, then U is, you can assume U is equal to zero. Then reflection wave is coming out. So depend on the absorption in the wall, the reflection velocity is of course changing. Could be less than U, the incident, the wave velocity. So if it's rigid, it's coming back with the same U as the incident, otherwise less than that. But again, the pressure experienced by the wall gonna be maximum twice of the incident shock pressure as we talk. Now let's move on here, and as you look at here, you're talking about incident pressure of a few hundred millibar, 1/1000th of 1 bar, and 1 bar is 14.5, around 14.7 psi. And as you look at the loading, situation, as you see here, is a time versus pressure. It's always for air explosion or gas explosion, which has a two triangular part. One of the good report is a technical manual developed by U.S. Army for the type of the pressure loading. This is mostly for air explosion situation, which is close to the gas explosion. One part, this is a reflection as a result of the reflection wave. This is due to the drag loading, drag pressure, which is really part of the incident shock wave pressure. Incident and reflection. So it's always like this duration for chemical explosion in air is very short, but for gas explosion, maybe not. And reflection wave comes here, then others just keep dragging. Incident shock wave. Initial the shock wave pressure before hitting the structure. So it's worth to keep that in mind, the basic loading pattern. Okay, couple of more minutes then. Damage level, you can really read. There is this is a blast overpressure effect on a vulnerable refinery part. All this part, you are dealing with the PSI, fraction of the PSI, which means it's, think of 14.7 as 1 bar. It's a fraction of the PSI. Window could collapse. The louvers is a ventilation openings, right? So that sort of the thing, piping breaks, roof collapses. That's sort of the items you can think of for the plant damage, okay? And this is translate into the chart. The damage of the building for internal explosions, progressive collapse could be like this. We involve in the naval vessel internal explosion. This is what exact such a situation is. Okay, and the guidelines you can read. The dominoes is talking about the domino effect, you know, which is part of the progressive collapse. Not much information, but talking. And people, effect on the people is here the description is very simple here. It said it's burnings, the fragments hitting the people, and building or other structure, the falling down. So there is no unknown kind of the injury to the people, but this is what another bad thing is this, the last one. Fragment is the most problem in the defense area. This is a kind of accidental situation, but in the defense area, the fragmentation artificially generate the fragmentation at the time of explosion, because at the time of explosion, not only shock is a problem, the shell is really break into pieces, just fly all over the place. So it try to kill the target as many as possible. That's a big problem nowadays. Bomb, in Second World War, when dropped a bomb, then it destroyed one particular area, no more. As you drop the bomb, then around the mid-air, it just explosion occurs, then fragmentation occurs, it just spread all over the place. So it kills many targets all in the same time. Okay, I think I'll stop right here. Lecture here is really very general, very dry, but that's what that is. And chapter 9, I'm going to cover Friday. And Monday, flag, and we'll move on to Undex, okay? And Undex is more comfortable to me. Okay, have a good day.